For today's class, we are going to look into chemical equilibrium, and here we have two keywords. Chemical, meaning we are dealing with chemical reaction at equilibrium. So when we talk about equilibrium is of two types. We have what we call static equilibrium and dynamic equilibrium. So for every chemical equilibrium, it can only be in what? In a dynamic equilibrium. So any time we hear the word equilibrium, it means there is a balance. So in a chemical reaction, we always have reactant and product. A reacts with B to give C and D. For any chemical equation or reaction to be at equilibrium, it must be reversible. That is one of the conditions. For us to attain dynamic equilibrium, the equation or the reaction must be a reversible reaction. For a balanced chemical equation, each of the reacting species will have a coefficient. Let's put it there. Alright. Now, before the definition of chemical equilibrium, first, what are the conditions that must be attained or fulfilled before a particular chemical reaction can said to be at equilibrium? Number one, like I said, it must be a reversible reaction, and number two, it must occur in a closed system. Being in a closed system means nothing will enter the system and nothing leaves the system. So if a particular chemical reaction is not reversible or the system is not closed, then it cannot attain stability. The third point, it must be dynamic, meaning there must be movement. In short, there must be chemical reaction. If there's no chemical reaction, there cannot be chemical equilibrium. So chemical equilibrium cannot be a static equilibrium. Then the reaction should be able to start from both sides. So it is not enough to start with A plus B to give us C before C plus D giving us A plus B. We can start with C plus D giving us A, then A plus B. So meaning it's not enough to start from this. You can always start from what? Each of the side. Let's just give an example. Let's consider the thermal decomposition of calcium carbonate, which can give us calcium oxide and CO2. If this is heated in a closed vessel, a closed system, whereby this CO2 cannot evolve, cannot go out, then under some certain condition, this can reverse to give us this. So initially we can have limestone, we can have calcium carbonate, then we decompose it thermally to give us this. Or initially we can put together calcium oxide and CO2 under certain condition, and we'll get what? Calcium carbonate. And this can also return to give us this. So either we can start from this giving us this, or we can start from these two giving us that. So this is an example of a dynamic equilibrium, which is what? Chemical equilibrium. The fifth point is that the concentration of all these species should be constant throughout. So it means the concentration of calcium carbonate, calcium oxide and CO2 should be constant. Same as their pressure for gases. And the last point, which is the most important point, the rate at which the reactant forms the product must be equal to the rate at which the product forms the reactant. And from there we get our definition. So the rate of forward reaction, meaning reactant to product, must be equal to the rate of backward reaction, the reverse direction. Now, what is now chemical equilibrium? So right, a chemical equilibrium is a dynamic equilibrium that involves a reversible reaction in which the rate of forward reaction equals the rate of backward reaction. Again, a chemical equilibrium is a dynamic equilibrium that involves a reversible reaction in which the rate of what? Forward reaction equals the rate of what? Backward reaction. Now let's give example of chemical equilibrium or chemical system at equilibrium. So this is one example. Let's write all that. So the oxidation of iron by passing it through steam to give us what? Iron oxide and hydrogen gas produced. The reaction between nitrogen and hydrogen to give us ammonia, and this is for the industrial preparation of this one is called the Haber process. Should be 3. Okay, this is contact process, which is used in preparation of sulfuric acid. Let's give one more. So all these are examples of chemical equilibrium. So whereby this can give us this, and we have the reverse case under certain conditions. Our last class we talked about the rate of chemical reaction. So here we have RF, rate of fall reaction, and backward reaction. So what is the connection between rate of chemical reaction, the concentration in terms of this balance equation? This will take us to the concept of what we call the law of mass action. So this law actually gives the effect of concentration on the reaction rate, and it was stated by Wage and Goldberg. So, and what's the law? The law of mass action states that at constant temperature, that's the condition, at constant temperature, the rate of reaction is proportional to the active masses of each of the reactants. Again, at constant temperature, the rate of reaction is proportional to the active masses of each of the reactants. Now, write that. The active masses in this case is usually expressed as the concentration of what? Of the reacting species. So for this one, for the fall reaction, according to the law of mass action, the rate of fall reaction is proportional to the concentration of A raised to the power of what? A. And also proportional to the concentration of B raised to the power of what? B. So that's according to law of mass action. So from here we can say rate of fall reaction proportional to what? Concentration of A raised to the power A, B raised to the power of B. From here, rate of fall reaction becomes, we have K into brackets A raised to the power A, concentration of B raised to the power B. So this K is called the velocity constant. This for the forward reaction. We can do the same, if you are going forward, A and B are the reacting what? Particles. But if you are moving backward, C and D are the reacting particles. So for the backward reaction, the rate of backward reaction is proportional to what? Concentration of what? C to the power of C, and the concentration of D to the power of D. From here, RB equals to K. Let me go this one, K1. K2 into bracket C raised to the power C, then D raised to the power what? D. So rate of forward reaction, rate of backward reaction. Now from this condition, the rate of forward reaction and the rate of backward reaction, they must be equal. So in that case, we can say the whole of this, which is K1 into bracket A raised to the power A, B raised to the power B, must be equal to K2 C raised to the power C, the concentration of D raised to the power D. From here, if we divide both sides by K2, so it implies that you can have K1 over K2 equals to concentration of C to the power of C, concentration of D to the power of D over the concentration of A to the power of A, concentration of B to the power of B. So this K1 over K2 is called, this ratio is called the equilibrium constant. So we can call the equilibrium constant K, BK. From there, K, which is our equilibrium constant, equals to what? That. Now, this equilibrium constant is very important. It's very, very important. So for a chemical reaction, this must be a constant. So meaning if we increase the concentration of the numerator, for this K to be balanced, the concentration of the denominator should also increase. If we decrease the concentration of C, for A must increase. If you increase this must increase. If you decrease this must increase. So anything that happens at the numerator must happen at the denominator to keep this K balance. Now, for a chemical equilibrium to remain constant, there are some conditions or constraints that we have to consider. Those constraints makes the equilibrium position to be fixed, makes the reaction to be at equilibrium. If one of those factors is altered, the equilibrium position will shift in order to annul that effect, in order to neutralize the effect. So for example, like I said earlier, if the concentration of any of the numerator is increased, then that of the denominator must also increase. So but in this case, the system will do that by itself, so as to ensure that K is constant. So come back here, we can say if the concentration of what C and D, or C is increased for example, then that of what A or B must also increase. So in that case, it means the position will shift to what? To A. Mean if you are adding more of what C, you will be producing more of what A and B. And if you are removing what C, A and B must also what reduce. So in that case, if you are removing C and D, the position will shift to the right, so that we also use upwards A and B to form what more C. And this will lead us to the next thing, which we call the Chateliers principle. Note, for this equilibrium constant, we use concentration when we are dealing with solution. So, but if you are dealing with gaseous species, we use their partial pressure. For example, in this case, we use their partial pressure instead of what concentration. But same things apply. Now let's move to the Chateliers principle. Before stating this principle, recall when we derived the formula for the equilibrium constant, temperature was kept constant. If temperature is altered, the position will shift. So there are two major factors that keep the equilibrium position fixed. Number one is the temperature. If temperature is altered, what happens? The position will shift. Secondly is the pressure if it's gas, or concentration if they are not gas. Now, the law state or the principle, this states that if any of the conditions of a system in equilibrium is altered, the equilibrium position will shift to annul or to neutralize the effect. And what are these factors? I've mentioned them: temperature, pressure, concentration. Now the first one, what's the effect of temperature change on the equilibrium position? So anytime we want to talk about temperature, we have to first know how does the change in temperature favors the reaction. So in this case, we have to talk about exothermic and endothermic reaction. So positive enthalpy change indicate that this is what endothermic reaction. And we know for endothermic reaction to take place, it must absorb heat from the surroundings. So it needs what? Heat. So if there is increase in temperature, it's going to favor what? Endothermic what? Reaction. Because it needs what? The temperature to proceed. So in this case, the equilibrium position will shift to the right whenever the temperature is increased. What if the temperature is decreased? Decrease in temperature will now favor the backward reaction. So it will move from what? To the left. So note this. For an endothermic reaction, increase in temperature will favor forward reaction, while decrease in temperature will favor what? Backward reaction. For example, so this particular reaction is endothermic. So if we increase the temperature of the system, you get more of what? NO2. And if the temperature is dropped, is decreased, we are going to form more of what? N2O4. What about exothermic? Now, for exothermic reaction, heat is what given out to the surrounding. So if you move forward, it means this is what? Exothermic. The reverse is what? Endothermic. So if we increase the temperature of the system, the reverse will be favored. The reverse or the backward reaction will be favored, because backward reaction needs what? Addition of heat, increase in temperature. So if we increase the temperature of an exothermic reaction, it favors the reverse reaction or the backward reaction. But if we lower the temperature, it's going to favor what? The forward reaction. For example, the oxidization of sulfur 4 oxide to source oxide in contact process is an example of what? Exothermic reaction. So if we want to produce more of SO3, we need to reduce the temperature. Because for exothermic reaction, decrease in temperature favors the forward reaction. But if we increase temperature, it's going to what? Favor the reverse reaction, which is what? Endothermic. Note, for this one, endothermic, so it means A plus B to C is what? Endo. But if you want to move from C backward, it's exo. So if the forward reaction is endothermic, then it means the reverse is going to be what? Exothermic. Now let's now move to the effect of change in concentration on the equilibrium position. Now let us consider the equation, the oxidation of iron. Now look at this particular reaction. When we are dealing with effect of change in concentration, we are less concerned whether it's endothermic or exo. We assume other conditions are constant. If we increase the concentration of steam, that is, we have more water, iron passes through more steam, the position will shift to the right. Why? Recall the formula for the equilibrium of constant. This reactant will fall under the denominator, this will be at the numerator. So if we increase the concentration of all this, for balance, the concentration of these two must increase. So as we are adding more steam, what happen? We are getting more what? Iron oxide and what? H2. So it's going to shift to the right. And if we decrease the concentration of iron or steam, if we decrease the concentration of this one, this must also decrease. And for this decrease, it will use up and it's going to shift to the left. So if we increase the concentration at the right hand side, at the left hand side, if we increase the concentration here, it will the position will shift to the right. We'll get more of this. If we remove this instead, it shifts to the left, we'll get more of this. So if you're adding to a particular side, you get more of the other side. If you are removing from a particular side, you will get more of that side you are removing from. So if more iron or steam is added, more of what? Iron oxide and H2 will be produced. So meaning if we want more products, we add to the reactant. And if we want more product, it's either if we want more product, it's either we add to the reactant or we remove that product. So if we remove what? H2, let's suppose what we desire is what? Hydrogen gas. As we remove H2 or the whole of the product, more of it will be formed, and this one will be smaller. So if you want more of this, we have to remove it so that more of it will be formed. So I think that's very clear. Put that one down in a way you understand. So move on to the next one. Next one is the effect on change of pressure. Before we can consider the effect of change of pressure, one of the reacting species must be a gas. So we can use this example we can use this one as an example. Before we can use the effect of changing pressure, like I said earlier, one of the reacting species, either the reactant product or all, should be in gaseous form. That is one. And secondly, if you look at total volume, at the right hand side and left hand side should be the same. What do we mean by total volume? This is 2 to 1. So 2 plus 1 is 3. This is 3 to 2. So if we move from left to right, there is decrease in volume. If we move from right to left, there is increase in volume. And recall that pressure and volume, they are inversely related. So whenever the pressure of the system is increased, it favors the side with lower volume. Now for this particular system, if we want to get more of the product, we will need to increase the pressure to get more of this. Because increase in pressure will favor the side with lower pressure. We can even use the concept of number of mole to explain. So we should not use volume this time around. We know the more the number of mole, the more the pressure. The more the number of mole, so here is 3 to 2. So the pressure here ordinarily is more than the pressure here. So this one has low pressure, high pressure. So if we increase the pressure, it will move to the side with lower pressure. And if we reduce the pressure, it will move to the side with higher pressure. Let us take another example. So this is 1 plus 3, 4 to 2. So if we want to get more of ammonia, we need to increase the pressure. We need to increase the pressure. Now for this particular one, we use one in contact process, yes. O2 is usually in abundance, oxygen from the air. Because this oxygen is from air. We have it in high volume. So this one in high volume, meaning we're having more about O2. So by default, we get more of this. So even if the pressure is not really increased, it can still yield like 98% of this. But for ammonia, hydrogen is not in abundance. So meaning the concentration of the reactant is not really much. So for us to have more ammonia, the pressure must be increased. In fact, the pressure has to be increased to about 200 atmospheric pressure before you can get what? About 18 or 20 something% yield. So it is important to increase the pressure of what? This, in order to get what? More of ammonia. In short, increase in pressure will favor the side with what? Lower mole, and decrease in pressure will favor the side with what? With higher number of mole. So before we continue, this particular process, we'll call it the contact process. And this process, we'll call it the Haber process. So you have to understand the following about Haber and contact process. In Haber process, our aim is to get more of ammonia. And this reaction is actually exothermic. So first, the industrial preparation of ammonia, this is called Haber process. Since it is an exothermic, for us to be able to get more ammonia, we need to reduce the temperature. If normally temperature of 700 degrees Celsius is needed for ammonia to produce, we have to drop it for the normal reaction to be at equilibrium rather. If at 600 degrees Celsius, this will be at equilibrium, meaning the rate at which ammonia is formed is same thing as the rate at which nitrogen and hydrogen gas are also formed. If at 600. To produce more ammonia, we have to drop it to about 400. So we decrease the temperature to get more ammonia. Next, we'll remove ammonia, because as we remove the ammonia, the concentration of the forward reaction decreases, then the position will shift to the right. So if we remove ammonia, more ammonia will form. So 1, we decrease temperature from normal. 2, we remove ammonia. 3, we add more reactants. If you add more reactants, if the concentration of the reactant increases, the position will shift to the right. Then, since they are both gas, we need to increase the pressure. Okay, I've said that because as we increase the pressure, it will favor the cell with lesser number of moles. Then lastly is the effect of catalyst. Note, catalyst does not have any effect on the equilibrium position, meaning it will not favor forward nor backward reaction. It will only increase the rate at which the forward reaction and backward reaction reaches hot. So for example, let's suppose before this can give us this, it takes 1 hour, and for this one to return back to this, it also take 1 hour. If there is a catalyst, it can take just 10 minutes from this to this and this back to this. So the catalyst only increase. Please note this. Catalyst doesn't have any effect on the equilibrium position. It only increases the rate of forward and backward reaction. So the catalyst we use in Haber process is what? Small pellets of iron. We use small pellets of iron in Haber process. Now let's move to contact process. We want to get more of what? Sulfur 6 oxide. So this side has less number of mole. So definitely we have to increase the pressure. That is one. The reaction is also exothermic, meaning decrease in temperature will favor the forward reaction. So pressure have to be increased to shift here. Then temperature have to be decreased to shift here. Then we have to remove SO3 so that we get more SO3, or we increase the volume of air so we get more SO3. And the catalyst used here is vanadium 5 oxide. Vanadium 5 oxide is the catalyst used there to increase the rate of what? Forward and backward reaction. Normally this ought to be the end of the lecture, but I want to make reference to something I made mention of during the lecture of acid, base and salt. I mentioned the Chateliers principle. So I think it will make sense if we make reference back to that also. But before this class, in our last class, I made mention of free energy. That for a reaction to be at equilibrium, the Gibbs free energy has to be minimum, has to be very close to 0 or exactly 0. So what is the connection between equilibrium constant, free energy, and electrode potential that we did in electrolysis? So what is the connection between free energy, electrode potential, and equilibrium constant? We talk about free energy under energetics, we talk about electrode potential under electrochemistry, and we just discussed about equilibrium constant. So what is the connection? Now first, according to the Chateliers principle, so when a system is at equilibrium, whenever any of the condition is disturbed, it adjusts. And this is because at equilibrium, the free energy change of a closed system at constant temperature and pressure is 0, meaning there is no net heat flow. So and no work is done. If it is not flowing, no work is done. So what is now the connection between the free energy, temperature, and equilibrium constant? So this is the relation between free energy, that constant temperature, equilibrium constant, and this R is the gas constant. So if this energy is not shifted, if there is energy and it is negative, so this minus will come to this minus. By the time we do the what? Reciprocal, I know this logarithmic function. So we are going to get what? The new value of K. So what about electric potential? Note, in electrochemical cell, we have two reactions occurring simultaneously. They are complementary. So that's oxidation and reduction occurring simultaneously. So that's the kind of what? Equilibrium position. Because in electrochemical cell and electrolytic cell, at the cathode there is reduction, at the anode there is oxidation, and they occur simultaneously. So that's the kind of what? Equilibrium. and the electric potential can be given in terms of what? The temperature, equilibrium constant, and the charge. So we know this F to be farad, this is number of mole of the charge, the R is gas constant, temperature, and K is the equilibrium constant. Now, the value of K is very important. So especially in electroplating industry, one of the uses of electrolysis. So for example, if you are coating lead, so if a coating of lead is to be deposited on an object, you want to coat a body with lead. So the higher the value of K, the higher value of K mean that the forward reduction is favored, resulting in what? A thicker lead coating. So that's under electroplating. So the more the value of K, the more the thickness of the lead that will be coated or any other metal on a. And from here we can get the relationship between the free energy and electric potential. How can we get that? Look at this. RT link K. RT link K. The only difference is that this one is minus. So what we can see, the free energy equals to minus this. So we replace, we can bring this minus here. If this minus here, we bring it here. So we can replace the whole of this, which is this, as this. Then we'll get this. By the time we cross multiply, the free energy becomes minus the electric potential NF. So this minus indicates that the reaction will be spontaneous because the free energy is less than 0. And in this case, it should not be at equilibrium again. So it means the chemical energy will be used up and we get more electrical energy. But if the electric potential is 0, then what happens to G? G also becomes 0. Then what happens? The ions will discharge and will recharge. Discharge and will recharge in the solution, and nothing will happen. The last thing we meant to talk about is acid-base equilibrium. We recall that when acid reacts with base, we get salt and water. With this arrow, it means it is not a reversible reaction, so we can't have equilibrium. But for some kind of acid or base based on their strength, we can have a reversible reaction. And anytime we have that reversible reaction, it means salt and water can give acid and base. Normally, when acid and base react to give salt and water are not meant to give acid and base. For example, if you have the titration of strong acid, strong base, the salt you are going to get to be neutral salt, and there is no how it's going to return to give us acid and base. But in a case whereby acid and base gives salt and water, and this salt and water can combine to give what? Acid and base. In this case, under solid condition, this will be at equilibrium. So this will call acid-base equilibrium. So the forward reaction is neutralization, while the reverse reaction is what we call the hydrolysis of salt. Meaning when you add water to salt, it gives us the acid and base, and the acid and base can reverse to give us salt and water. So, but they are the kind of salt that can be hydrolyzed to get what? To give us acid, base, and salt. What are those salts called? If you can remember, they are salts whose pH is not 7. Acid has a pH less than 7, base has pH greater than 7. The salt is expected to be neutral with pH of what? 7. But we have some salts whose pH can either be more than 7 or less than 7. So, and they are salt got in either when we have strong acid with weak base, or weak acid with strong base, or both weak acid and weak base. So all the salts form in this case, they can be hydrolyzed and they form a system of kind of what? Equilibrium. So let's recall during the titration of strong acid and strong base. So what are the indicators used based on the neutral point? So this is the reaction of strong acid, strong base. The salt formed here cannot undergo hydrolysis. This strong acid, strong weak base. Then here we can have salt that undergo hydrolysis. We give an example. Same as weak acid, strong base. When I have weak acid, strong base, the salt that will be formed in this case, they will have pH greater than 7. If you have strong acid, weak base, the salt form will have a pH that is what? Less than 7, greater than 7. So if you have weak acid, weak base, what will happen? Okay, but before I answer that question, sometimes you can be given this graph and ask which of these graph represents strong acid, strong base, or weak acid, weak base. Just note, if the neutral point is between is greater here, is more than 7, it's between a value greater than 7, here is about 9.5, to a value less than 7, 6, 7, 6, 5, 4, this is 3.5. So it ranges from 3.5 to 9.5. So this is definitely stronger strong base. So because it takes some range in strong basic medium and acidic medium. But in this case, if you look at this, it's below 7. Between 7 and what? 1, 2, 3, 3.5. So this is definitely strong acid. So that's why the pH shifts to this point. So the neutral point falls below here. And if the neutral point falls above, 7, 8, 9, 7, 8, 9, 9.5. 7 to 9.5. So in this case, it is what? Strong base. It is what? Strong acid. For this one, we have strong base, strong acid. So I say strong acid, strong base. This one is what? Strong acid, weak base. This one is what? Strong base, weak acid. For this one, it has no sharp point. The sharp point is unnoticed. So most times during titration, the volume of what? Acid is usually in 25 what? cm3. We titrate a certain volume of acid with what? 25 cm3 of base or 20 cm3 of base. Why this stand for the pH of the solution? The answer is yes, the salt can undergo hydrolysis. So what will be the pH? Will it be less than 7 or greater than 7? It depends on what? On Ka and Kb. What is Ka? What is Kb? So Ka is called the acid dissociation constant, while Kb is the base dissociation constant. Or we can call it acid power and base power. So if Ka is greater than Kb, the pH is going to be less than 7. But if Ka is less than Kb, the pH will be greater than 7. And when Ka equals to Kb, then pH is 7, meaning the salt will be neutral. So for some weak acid, weak base, the salt form can be neutral, can have pH less than 7 or greater than 7. But we only use Ka and Kb to describe strong acid, strong base. So for weak acid, weak base. Strong acid, strong base, we don't use what? Acid dissociation constant and base dissociation constant because they do not undergo hydrolysis. Mainly because they are conjugate ions. For example, in sodium chloride, sodium and chlorine ions are weak, so that they do not hydrolyze at all. So for these three cases, we do not use the acid power and base power. Since only one ion hydrolyzes, so one constant matter. So no need for Ka or Kb. For example, sodium chloride is neutral to litmus because it is formed from strong acid, strong base. So the sodium here and the chlorine here form the sodium chloride. So this has a pH of 7. Ammonium chloride, however, has a pH which is less than 7 because it is formed from a strong acid and a weak base. We can also use aqueous ammonia. So in this case, we are having this from weak base and Cl from strong acid to give what? NH4 plus. However, sodium ethanoate is formed from a strong base and a weak acid. So to have a pH greater than 7. Now, consider the following salts formed from weak acid, weak base. Ammonium ethanoate formed from what? Weak base and weak acid has a pH less than 7. Why does it have a pH less than 7? Because Ka is greater than Kb. Then we have sodium ethanoate. But before that, further study shows that these two, their Ka and Kb, they are very close. So the pH is actually 7. So it's under this case. Although Ka is slightly more than Kb, but in this case, they are almost same thing. So it will have a pH of 7. But for ammonium cyanide, that will be Cn here. It falls under the 7 case. The pH is what? Is greater than 7 because Ka is less than Kb. Then for the first example here, we have a salt, and that is ammonium fluoride. It has a pH less than 7 because Ka is greater than Kb. Back to acid-base equilibrium. Before I continue, just note that the hydrolyzation of salt depends on either if there was a strong acid or a weak acid or a weak base during the formation of that salt. So let's consider the ionization of the following weak acid or weak base. So according to Arrhenius theory, so we are going to be having H3 plus A minus, because from HA this means H plus A minus. So this H plus is hydrogen with M meter. It will create a covalent bond with H2O to form H3O plus. We've done this already. Now the equilibrium constant for this particular ionization is Ka. I was referring to the other time. And if you follow the law of mass action, we can write the equilibrium constant as thus. So I call this the acid dissociation constant, or we can simply call it the acidity constant. Note, we are referring to a weak acid here because weak acid the ionizes partially. Let's do the same thing for the basicity constant, or we'll call it the base dissociation constant. So we can use Brocellari. This water is what? Proton acceptor. So this is like a base, this is an acid. So in this time around, the base will be known to accept the proton. In fact, in this case, this is what? The base, this is the acid. This is the acid, this is the base. I will call this the conjugate acid, this is the conjugate base. You've done that already before now. So what will now be Kb? The basicity constant, or call it the base dissociation constant. Yes. Now, Ka and Kb, they can either have a very small value or they have a very large value. So whenever they have small value, it implies that the concentration of the unionized molecule is relatively larger compared to those that ionize, meaning they ionize weakly. So numerator are those that ionize. This one are those that don't ionize. So if Kb is small, it means this one is very high, then this one is small. This one is small, this one is also small. But if Ka or Kb is very high, it means the amount that dissociate is very more, and the amount that are undissociated, they are very what? Less. So in this case, if Ka and Kb are small, it means this particular acid and base here, you can call them weak electrolytes. And for hydrolysis to occur, Ka or Kb must be strong. And I've explained that earlier. So it's either we have weak base, then strong acid, or weak acid with strong base, or they are both weak. But if Ka and Kb are both what? Strong, then hydrolysis cannot occur. Now let's talk about water itself. According to Brocellari theory, this water is a base because it accepts proton. So this is a base. Why this water is an acid? Well, it donates proton to this one so that it loses proton. So proton donor are called acid, while proton acceptor are called what? Base. So this is an acid, but here it becomes a conjugate what? Base. So in this way, it means water can be acid and water can also be base. So water is considered to be a weak electrolyte. So it means water can dissociate or ionize to give us H plus and OH minus. They are both weak, so it is reversible. And if you have extra water here, if you add water to it, so it becomes H3. plus, so this one will be 2, and this one becomes H3 plus, H3O plus. So for water, the equilibrium constant of water can be written as what? The concentration of this multiplied by what? That of this over the other ions here. So put it this way. And experimentally, Kw has been measured under certain conditions. So another name for the equilibrium constant of water is also what we call the ionic product of water. So for a pure water that doesn't contain any impurity at 25 degrees Celsius, so the ionic product is actually 1 times 10 raised to the power minus mole per dm cube. Meaning, if you have 1 dm cube of water that is pure with no impurity at 25 degrees Celsius, the ionic product is 10 raised to the power minus 4. And at neutral point, they have to be equal. This will have to be, the concentration of what? H3O plus and OH minus must be the same. And for it to be the same, using law of indices, this will what? 10 to the power of minus 7. This also what? 10 to the power of what? Minus 7. To give us 10 to the power of minus 14. We've done this already under acids and salts, so consider this as a revision. So this indicates that a neutral solution is the one in which the concentration of what? Hydrogen ion and hydroxide ion are exactly the same. So a solution will be acidic if the concentration of this one is small than that of this. So meaning this power, what we have here can be 10 to the power of, let's say, minus 4. To retain this would be what? 10 to the power of minus 10. So it means this one value is higher than this value. So for this particular one, it is what? Acidic. And it's going to be basic if the concentration of this is smaller than this. So this can be 10 to what? Power of, let's say, minus 4. And this is what? 10 to the power of what? Minus 10. No, you might be wondering, this one is 10. 10 is bigger than 4. So this one should be higher. No. For this actually means reciprocal. 1 over 10 to the power of 10. So this about 1 over 10 billion. This is about 1 over 10,000. So 1 over 10 billion is smaller than 1 over 10,000. So, and same thing goes for this. So for acidic solution, the concentration of what? H3 plus is small. While for basic, this one is what? Is small. And for a neutral solution, they are equal. Now, working with all these numbers can be a bit complex. So what if we neglect this minus sign and the 10 itself? We consider just 7, 4, and 10. Something becomes obvious. So 7 becomes the baseline, neutrality. A value less than 4 indicates what? Acidity. A value greater than what? A value less than 7, acidity. A value greater than what? 7 is what? Basic, in this case, like this 10. And the maximum we can have is for the concentration of the acid to be what? To be 0. And in that case, we'll be having 10 to the power of 0 here. So in that case, this will be what? Minus 14, this will be 0. So meaning the maximum can have is 0 and the minimum is what? The maximum is 14 and the minimum is what? Is 0. So meaning the range is from what? 0 to 14. So anything between 7 and 0 acidity, anything between 7 and 14 basicity, basic. So and that's how pH scale is formed. And recall, what is pH? pH is just what? If you take this coefficient or if you take this number, and mathematically it is what? Negative logarithm of the concentration of hydrogen ion to base 10. So if you take negative logarithm of this to base 10, we get what? 7. For this one we get 4. For this one we get 10. And this is the basis of what? Of pH. And the pOH is opposite. For pOH is what? Minus logarithm to what? Concentration of what? OH minus, as we have it there. Well, we should know that the value of pH of a solution plus the pOH is what? 14. So meaning if the pH of a solution is 3, the pOH has to be what? 11. For us to get 14. But for for general convention, most times we do talk about what? pH. So if you are given any concentration, you can always get the pH. And if you know the pH, you can always get the pOH. Now consider these two examples. Calculate the pH of 0.0001 molar H2SO4 and also calculate the pH of what? 0.001 molar sodium hydroxide. Now, H2SO4 is an acid, and its aqueous solution will give us H plus and SO4 2 minus. I meant to balance 2. So this means 1 mole of H2SO4, we have what? 2 moles of H plus. So this is concentration for 1 mole. That's why it's called mole per dm cube. For 2 moles, what will be the concentration? So the concentration of H plus here is actually what? 2 times what? 0.001. So this means mole per dm cube. So meaning the concentration here is, let's write in standard form. That's 2 times 10 raised to power minus 3. So what's pH? pH is negative logarithm to base 10 of what? 2 times 10 raised to power minus 3. So if you apply the law of logarithm, this minus, you can take it out. That's minus. Then if you have log A times B, that's addition. So law of logarithm, that will be log 2 base 10 plus log minus 3 base 10. Sorry, log 10 power minus 3 rather. These two here, then 10 power minus 3 here. So what next? The pH equals to minus, what's log 2 base 10? So you can press that in your calculator. But for, sometimes you might not be given calculator. If you are not given calculator, for example in JAM, and you need to calculate this. So there are some basic log you must know by heart. Log 2, log 3, and log 5. If you know these 3 log by heart, most of the numbers you be given, you can actually get their value by using what? Laws of logarithm. For example, if you are told to look for log, let's say log 12 base 10. So we know that 12 is in ppf. Point product factor, 2 here is 6, 2 here is 3, 3 here 1. So that's 2 raised to power 2 times 3. So you must learn how to transform number to this. This from knowledge in primary school. This raised to power 2 times 3 base 10. And this equals what? Log 2 base 2, log 2 raised to power 2 base 10, plus this times plus log 3 base 10. Then these 2 goes to the back, law of logarithm. 2 log 2 base 10 plus log 3 base 10. So then you can express log 12 as this. So if you know the value of log 2 and the value of log 3, you can know log 12. So most number, so you have to know the value of these 3 logs. So log 2 is 0.3010 and log 3 is 0.4771 and log 5 is 0.6990. So from here, so log 2 base 10 is 0.3031 plus, what happened according to law of logarithm? No, if I have log a raised to power m base b, so this m goes to the back and this becomes m times log a base b. So this means what? This minus 3 goes to the back. That will be what? Minus 3 is done to, so log 10 raised to power minus 3 base 10 is written as what? Minus 3 log 10 base 10. And log 10 base 10 is what? Is 1. So the answer is what? Minus 3. So the pH becomes negative 0.3031 minus 3. You can easily press down your calculator on this. You get minus 2.6969. Minus is plus. So the pH equals to plus 2.7 approximately. 2.70 in 2 decimal places. So please note all this. Note this. Then let's do the second one. Note, we are looking for the pH of a base. So this actually giving us what? Concentration of the base. So you have to be very careful. The aqueous solution of sodium hydroxide will give us Na plus OH minus. It's already balanced. So from here, it means the concentration of OH is when we are given to what? 0.001 molar or mole per dm cube. Note, suppose we are having, let's say, calcium hydroxide. By the time we balance this, we'll be having Ca plus OH. But this one is not balanced, so we must put 2 here. So in that case, any concentration we are given here, we have to multiply by 2, just like what we have here. So let's continue this. So if you are given the OH minus concentration, the best is to first get the pOH. And what's pOH? Similar. Negative logarithm to base 10 of the concentration of what OH minus. Always try to express in standard form. In standard form, 1, 2, 3. This is 10 raised to power minus 3 molar or mole per dmq. So pOH here becomes minus log to base 10 of what? 10 to what? Minus 3. So here pOH equals to, this one will go to the back. Initially we have minus here, you can write as minus 1 times, this thing will go to the back, minus 3 log 10 base 10. Log 10 base 10 is 1. Minus 1 times minus 3 is 3. Log 10 is 1, so the answer is what? 3. So it means the pOH is 3. But the question says find the pH. Remember, pH plus pOH is 14. Then the pH we are looking for, pOH is 3, is 14. Then pH equals to 14 minus 3. Then the pH is 11. So that's the pH of that base. So from the pH scale, it will show 11. So meaning it is what? It is a base. Now very brief. When acid reacts with base, we form salt and water. This neutralization, and this only occurs if an appropriate amount of acid is added to the base. Then at the end, the pH should be 7 for strong acid, strong base. But it is possible we have strong acid, strong base, and the pH is not going to be 7 if we didn't add the appropriate amount of acid to the fixed volume of base. So the resulting solution will have a pH which is not 7. How can we get that? Let's take an example. Now look at this question. 50 cm cube of 0.10 mole per dm of HCl solution is mixed with what? 50 cm cube of 0.15 mole per dm sodium hydroxide solution. What is the pH of the resulting solution? Don't say 7, because in this kind of reaction, neutralization may not occur. First, let's try the balance equation between HCl and sodium hydroxide. So we have NaCl plus H2. So what's the mole ratio of the acid? It is 1 to 1. So if we have 0.1 mole of the acid, it should react to 0.1 mole of what? Of the base. So but what's the number of mole in this solution? We don't know. Let's calculate. So this is concentration, not mole. I recall that mole is concentration times volume, but the volume must be in dm cube. If it's a cm cube, you divide it by what? 1000. So we can look for the number of mole of the acid, HCl, and number of mole of what? Of the base, NaOH. And what's the mole? The concentration. For HCl, that's 0.1. The volume is 50, that's times 50 over 1000. While this one is what? 0.15. The volume is also 50 over 1000. By doing this, we get the number of mole of the base and the acid to be this. But there's a problem. Look at this. The number of mole ought to be 1:1. But what are we having? This one is smaller. We have more number of mole. So the base is more than the acid. So since HCl has lower amount, so it means, for example, let me break this down. If we have, let's say, 5 HCl and we have, let's say, 3 NaOH, so it means we are going to have HCl 5 times. HCl. We also have NaOH. So for every HCl, it's tackle this. So what happened? This remaining 2 HCl is useless. Why? Because NaOH has been used up. So this NaOH in this case is called the limiting reagent. So this one will remain unused. So the one that has lower amount is the limiting reagent. In this case, HCl has lower amount. So it is the limiting reagent. So just like the example I gave, we are going to subtract. So 0.05 HCl will react to 0.005 sodium hydroxide. The remaining will remain in the solution. So at the end of the day, the concentration of sodium hydroxide that will remain unreacted is going to be different. 0.0075 minus 0.0050, and that will give us 0.0025 mole. That is the, sorry, not concentration, the number of mole of what? Sodium hydroxide that will be left unreacted because it has no more acid to react with it to neutralize it. So in this case, neutralization will not occur because the amount of acid is not much. We need to add more acid for neutralization to occur. Don't forget the question. We want to get the what? pH of the resulting solution. Before I can get pH, we have to know the what? Hydrogen ion concentration. So now we know the mole, we can calculate the concentration. If mole equals to concentration times volume, then the concentration equals to number of mole over volume. So the concentration of NaOH in that solution is going to be what? 0.0025 over, now what's the mole? What's the volume now? That will be the total volume of the whole solution. So in that solution, all the acid disappear, then the base will be left, but the total volume remains what? 50 plus 50, 100. So 100 cm cube. Inside 100 cm cube, 0.0025 mole is for what? NaOH. So that will be what? 100 cm cube. What I told you, the volume must always be what? dm cube. If you are given volume with cm cube, now the volume in cm cube is 100. Then the volume in dm cube will be what? 100 divided by 1000. That will be 100 divided by 1000 or times 10 to the minus 3. So from cm cube to meter cube, divide by 1000 or multiply by what? 10 raised to power minus 3. And from here, we are going to get the concentration of sodium hydroxide to be 2.5 times 10 to the power minus 2. So in this case, it means, and for NaOH, if it dissociates, it gives us what? Na plus OH minus. So the number of mole of OH minus here is 1. So it means the concentration of the OH minus is what? 2.5 times 10 to the power minus 2. So what can we get here? We can get the pOH. What's the pOH? pOH is a negative logarithm to base 10 of the concentration of OH, which in this case, our pOH becomes minus log to base 10. What is the concentration? So this time around 2.5. I will not use decimal. So in mathematics, 2.5 times 10 to the power minus 2 is same as 25 times 10 to the power minus 3. So that this is under standard form. So this will be same as what? 25 times 10 to the power minus 3. So using law of logarithm, our pOH here becomes minus, that will be log 25. Log 25 base 10, we turn the times to plus log minus 3 base 10. What's 25? 5 squared. But this 5 squared is it's unuseful. So what happens? These two will go to the back, and this will give us minus, these two goes to the back of the log. 2 log 5 base 10. Then this minus 3 multiplied, so that will be minus 3 log 10 base 10. Log 10 base 10 is 1. So from here, the pOH equals to minus. Now, already I told you should know log 2, log 3, and log 5. From what I gave you, log 5 is 0.6990. So 2 multiplied by what? 0.690. And that will be 1.398. Log 10 base 10 is 1. 1 times 3 is 3. So this equals to 1.398 minus 3 will give us 1.602. That's, sorry, minus what? 1.602. Minus give us plus. So it means the pOH equals to 1.60 into decimal places. But what are we looking for? We are looking for the pH. And what's pH? Since pH plus pOH is 14, to get the pH, we remove the pOH from 14. That will be 14 minus 1.60. And that is what? 12.4. So the pH is what? 12.4. It has no unit. It's just a number. That is the final answer. And this makes sense. Why? Because the resulting solution is meant to be what? Basic. You should have a pH greater than 7 because we have excess base due to the fact that what? The amount of the acid is limited, the limiting reagent. This is where we are going to end the class. And recall again, we can only have hydrolysis when we have weak base or weak acid. Either one of them is weak or they are both weak. And also remember, I explained the concept of buffer solution. It is a solution that resists change in pH when a little acid or base is added to it. So they are actually a solution containing weak acid and their salt, or weak base and their salt. So when we get to solubility, we are still going to touch the concept of what? Chemical equilibrium. Majorly for salts that are sparingly soluble in water. See you in my next class.